In this segment, we talk about why we use LU decomposition method. The reason why we have to talk about why we use LU decomposition method is because LU decomposition method is very similar to Gaussian elimination. And also the components of LU decomposition method are derived from the Gaussian elimination method. So one would surely ask the question that why do we use LU decomposition method? So to recap, if we have a set of equations like ax equal to b, what we first do in Gaussian elimination is use forward elimination steps to reduce the set of equations where the coefficient matrix becomes an upper triangular matrix. And the reason why we do that is because now we can conduct the steps of back substitution and be able to find out what the unknown variable or the unknown vector x is. The same thing is in LU decomposition method. What we do is we decompose the coefficient matrix A into L times U. And we already know that in order to be able to decompose the matrix A into L times U, we use the steps of forward elimination of Gaussian elimination to do it. Once we have done the decomposition, we set up the problem with L times Z equal to B to do the forward substitution, and we find Z. Once we found Z, we use that as the right hand side, and we use back substitution just like in Gaussian elimination to calculate the unknown vector x. So what you're basically seeing here is that there's a lot of similarity between LU decomposition method and Gaussian elimination. And to a layman, one might say that hey, LU decomposition method has 3 steps, while Gaussian elimination has only 2 steps. Isn't LU decomposition method more complicated or more complex than Gaussian elimination? So we want to be able to see that hey, whether the complication is there or not, we want to see that whether LU decomposition method is computationally efficient in Gaussian elimination or not. If it is not, then we might be simply wasting our time. In order to make the argument that how much time Gaussian elimination or LU decomposition method takes, what we need to do is we need to figure out what the individual components of these methods take so far as the computational time is concerned. Here is back substitution, which is common between the two methods. This is the end equation which we get at the end of the forward substitution step in LU decomposition method, or at the end of forward elimination in Gaussian elimination method. And this is the algorithm in order to be able to conduct the back substitution. What I'm giving you here is the code which is needed to be able to do the back substitution in MATLAB, let's suppose. And the computational time will depend on how fast the machine is, right? And it will also depend on how many computations you're doing, how many floating point operations are you doing. So let's take care of the first concept, which is the clocks, something called the clock cycle time. So if you have a 2 gigahertz machine, let's suppose, in that case, that means that it is going through 2 billion cycles per second. So how much does one cycle take so far as the time is concerned? It's 1 divided by 2 times 10 to the power 9 seconds, which is 0.5 times 10 to the power minus 9 seconds. And that's about 0.5, that's 0.5 nanoseconds. So the machine is taking 0.5 nanoseconds to go through one cycle, and the floating point operations which are taking place in this algorithm, they are right here. The division is taking place right here, the subtraction is taking place here, the division is taking place right here, the multiplication is taking place here, and it's taking place in 2 nested loops, as you can see right here. How many of these floating point operations are taking place, we won't be concerned about that in this particular lecture. It is given in a blog, and the link to that blog is given in the YouTube description, so you can definitely go there to satisfy your curiosity. But what we find out is that if we go through this algorithm right here, the number of multiplications, addition, division, and subtractions which are taking place are as follows. You have n divisions, you get 0 additions, You have n times n minus 1 divided by 2 multiplications, and you have n times n minus 1 divided by 2 subtractions. Those are the number of floating point operations which are taking place in the above algorithm. Now what we want to be able to figure out is that since we now know the number of floating point operations which are taking place, how much time is going to take to do back substitution, which are basically we are trying to derive this particular formula right here. So in order to do that, what we can do is we can say, hey, let's suppose if I know the architecture of the chip I'm using on this 2 gigahertz machine, let's suppose it's an AMD chip. And there's a typically AMD chip, it takes 4 clock cycles to do one addition. It takes 4 clock cycle times to do one subtraction. It takes 4 clock cycles to do one multiplication. And it takes 16 clock cycles to do one division. So if that is the amount of time it takes to do one floating point operation of addition, subtraction, multiplication here 4 times t, t is the clock cycle time, and 16t for division, t being the clock cycle time again, then the total time our back substitution is going to take is based on that, hey, we already know that we have n divisions, right? If we have n divisions and each division is taking 16 clock cycle times, that will be plus 16t. We already know that no additions are taking place, so it will be 0 times 4t. We also know that there are n times n minus 1 divided by 2 multiplication taking place, and each multiplication takes 4 clock cycle times. And then we know that there are n minus n times n minus 1 divided by 2 subtractions taking place, and each subtraction is taking 4 clock cycles. So if we add all those times, we get t times 4n squared plus 12n. So that's how we are able to obtain the computational time for back substitution. So we just found out that, hey, the amount of time it takes to do this particular back substitution is t times 4n squared plus 12n. Similarly, if you follow the algorithm, you'll find this is the amount of time it takes to do forward elimination. This is the amount of time it takes to decompose coefficient matrix A into the form L times U, and this is the amount of time it takes to do forward substitution. So we should be able to use these particular computational times of the various steps to be able to make the comparison between Gaussian elimination and LU decomposition method. As a side note, I want you to think about two things. One is that look at the forward elimination computation time. It is proportional to n cube. So is the decomposition to the L times U. It is proportional to n cube. However, the proportionality for the back substitution and the forward substitution is only proportional to n squared. So keep that in mind to figure out that, hey, which part of the algorithm is going to be computationally intensive. The other thing which I want to point out here is that look at the time it takes to back substitution and the time it takes to forward substitution. A person would think that, hey, these two times should be exactly the same, because what is forward substitution? It is the inverse of back substitution. In the back substitution, you start with the last equation and go to the first equation. In the forward substitution, you start from the first equation and go to the last equation. But the times are different. So think about it. Why are the times different? Second, look at the forward elimination and decomposition to LU. We use forward elimination to decompose our matrix into A times LU. However, the time for decomposition is less than the time it takes for forward elimination. So answer this question. Why is the time it takes to decompose the A matrix to L times U less than what it takes to do forward elimination? So answer those questions, and I think you'll have a better understanding of what we mean by computational times. So is LU decomposition more efficient than Gaussian elimination? Let's go and see. So T is the clock cycle time, and then if we have this as our size of the matrix, it's n equation n unknowns, so the coefficient matrix will be n by n. So in this particular case, what you will find out is here is that you have forward elimination. This is the amount of time it takes to forward elimination. This is the amount it takes to back substitution. So for Gaussian elimination, the time will be, hey, how much time does it take forward elimination? How much time does it take to do back substitution? So far as the LU decomposition is concerned, I have to add the time it takes to decompose the matrix, the time it takes to do forward substitution, and the time it takes to do back substitution. So this is the amount of time it takes to do Gaussian elimination. This is the amount of time it takes to do LU decomposition. So if we add those times, this is what we get for Gaussian elimination and this is what we get for LU decomposition, and you can clearly see both these particular times, computational times, are exactly the same. So both methods, LU decomposition method and Gaussian elimination, are equally efficient. So one should surely ask the question that, hey, so what is the advantage of LU decomposition method when it is so similar to Gaussian elimination, and it seems to be it is 3 steps rather than 2 steps. In Gaussian elimination, we conduct forward elimination, back substitution. In LU decomposition method, we do decomposition of the A matrix, we do the forward substitution, we do the back substitution. So what gives? That's what we want to answer as the question. So let's figure out, when is LU decomposition method better than Gaussian elimination? LU decomposition is better than Gaussian elimination when you have multiple right hand side vectors. What does that mean? What that means is that, let's suppose somebody gives me a set of equations ax equal to b and then says, okay, solve for x. So I solve for x. Then they give me another vector for b and keep the a to be the same and say solve for x. I can do that by either of the methods, and I can continue to do this depending on how many different right hand side vectors are given to me. So let's suppose if I'm given m right hand sides. So I'm given m right hand side vectors. How much time is it going to take me to do forward elimination would be given by that, hey, it will be, I'll have to do the forward elimination, I'll have to do m times, and I'll have to do the back substitution m times. That's the amount of time it's going to take me to do it by using Gaussian elimination. How much time is going to take me to do it by using LU decomposition method will be, hey, I'll do the decomposition, but then I'll have to do the forward substitution m times because my right hand side vector is changing, and also I'll have to do the back substitution m times. Now you might say, hey, why didn't I multiply this by m? Is because the decomposition of the A matrix will stay the same no matter how many times different right hand sides are given to you, because the A is not changing. So it is decomposition of L times U is not changing. You can decompose it m times, but you're going to get the same answer again and again. So in order to save time, you just do it only once. So now I'm hoping that you are able to see that why LU decomposition method is a better method than Gaussian elimination under these circumstances that multiple right hand sides are given to you. In order to exemplify this advantage, let's take an example of finding the inverse of a square matrix to show that how much time we are really saving by using LU decomposition method over Gaussian elimination. If you recall your definition of the inverse of a matrix, what is it? If I want to find the inverse of A, if I multiply it by its inverse, it should come out with the identity matrix. So what does that mean? What that means is that if somebody is saying that, hey, go ahead and solve for the inverse of a matrix, it simply means that you are setting up n sets of equations. You are setting up n sets of equations. That's what you're setting up. Why is that? Why is that? So is that if you are trying to find, look at this, A times B. B has n columns in it, and as you know that when you're solving a set of equations, you can only solve for one column at a time, right? So the A matrix multiplied by the first column of the inverse matrix will be the first equal to the first column of the identity matrix. The A matrix multiplied by the second column of the inverse matrix will be equal to the second column of the identity matrix. And if we continue to do this, if we go to the last column, the A matrix multiplied by the last column of the inverse matrix would be equal to the last column of the identity matrix. And what you're finding out here is a good example that whenever you are trying to find the inverse of a matrix, it boils down to finding the solution to a set of equations where the right hand side vector is the only thing which is changing. The A matrix in all of these sets of equations is always staying the same. Hence, what that means is that when I decompose my A matrix, I will only have to do it once. Let's see what that means. What that means is that if I was going to do the problem by Gaussian elimination, then since I have n different right hand sides, I'll have to do the forward elimination n times, I'll have to do the back substitution n times. And if I do the calculation, this is the total amount of time it will take me to find the inverse of a square matrix by using Gaussian elimination. And look at the computation time. It is proportional to a quantity of n to the power 4. However, when I'm doing LU decomposition method, I have to decompose the matrix only once. However, the forward substitution will have to be done n times and the back substitution will have to be n times. Why? Because I got n different right hand sides. And once I do the addition of these three quantities, this is what I get. And look at this. The computation time taken by LU decomposition method is proportional to n cube as opposed to n to the power 4 for your Gaussian elimination method. And I'm hoping that by looking at these expressions here for the time taken by Gaussian elimination, the time taken by LU decomposition method, that you are able to see that hey, there is a distinction between the amount of time it takes to find the inverse by these two different methods. To illustrate it, this is what you can see right here. This is the total time taken by Gaussian elimination, which we just found out. This is the total time which it takes by using LU decomposition method, which we just found out. And now if I had to find the ratio between the computation time it takes to find the inverse of a matrix by using Gaussian elimination to the computation time to find the inverse by LU decomposition method, all I'm doing is I'm dividing this quantity by this quantity. That's all I'm doing. And I did it for different values of n. And you can see, let's suppose if I'm trying to find the inverse for 10,000 by 10,000 matrix, the computational time it will take me to find the inverse by Gaussian elimination will be about 2,500 times what it will take me to find by LU decomposition method. Let's suppose, so to give you some perspective, let's suppose it takes 1 second to find the inverse of the 10,000 by 10,000 matrix by using LU decomposition method. It will take 2,501 seconds to do it by Gaussian elimination. And 2,501 seconds is approximately 41 minutes. So what you're finding out is that, hey, if it's going to take 41 minutes for me to find the inverse by Gaussian elimination as opposed to 1 second by LU decomposition method, you know where the your priority should lie. The general formula for large n, so far as the proportion of the time, ratio of the time is concerned, it is n divided by 4. As you must have seen here, that for 1,000 it's about 250, for 10,000 it's about 2,500, for 100 it's about 25. So that's what that comes from, that for large n this is approximately n divided by 4. You can derive it, of course, because for large n the amount of time it takes to find the inverse by using Gaussian elimination is this quantity right here, and then the amount of time it takes to do LU decomposition, because n is large, we can get away with taking only the first term of that expression, and this one turns out to be n divided by 4. So that's where that comes from. So I'm hoping that by listening to this particular lecture that you are able to see that in the first instance, when you look at it, you think that LU decomposition method is just like Gaussian elimination, maybe even more complicated or maybe more complex than Gaussian elimination. Why do we learn this particular method is that because when you have multiple right hand sides, such as when you're trying to find the inverse of a matrix, it is a computationally more efficient way of finding the inverse of a matrix than by using Gaussian elimination. And that is the end of this segment.